Hello, everyone. I wanted to talk about section 2.1, Early Ideas in Atomic Theory. Again, I'm going to be scrolling through your textbook as we discuss this, in part because there's some ideas from different parts of this section that I want to address maybe in a different order than your textbook does. So I think having it open makes that fairly clear. So the learning objectives are first of all, state the postulates of Dalton's atomic theory, and then secondly, use postulates of Dalton's atomic theory to explain the laws of definite and multiple proportions. So I'm going to actually start with those laws because the theory itself is based upon those laws. These laws were known before Dalton's theory was proposed, and it was only with that knowledge that he was able to propose that theory. So we're going to kind of skip down towards the bottom and talk about these laws. So you might remember from the module 1, we talked about compounds as being something that contain elements in a specific proportion. So when we have a compound, we can write a chemical formula for the compound. So we can write, for example, H2O, telling us that we have twice as many hydrogens as we do oxygens. This is called the law of definite proportions. So this is actually a scientific law. And as we described in Module 1, being a law doesn't mean that Dalton or someone else is there enforcing that that's true. What it means is that it is true. It is always true that in a compound you have these definite proportions. So in any sample of water you have that ratio, and if you have something other than that, that just means there's an impurity that you can go through a process of purifying the water to remove anything else that's present, and you get to that proportion. So that's the law of definite proportions, sometimes called the law of constant composition. So we're looking at a more complicated example than water here, isooctane, and we're showing that in a variety of samples we have an amount of carbon and an amount of hydrogen, and those amounts you can see are different from sample to sample. But when we divide them, we get the same mass ratio each time of 5.33 grams of carbon per every gram of hydrogen. Now don't remember that. Don't worry about remembering that specific mass is true for that substance. And in terms of the math that they're showing here, we'll be doing a version of that math in Module 3 based on the mole concept. So that is more useful to us than just using masses. They didn't know about the mole back then. So that's why these are shown in terms of mass. So that's one of them, the law of definite proportions. And then the other one is the law of multiple proportions. So this sounds like it might be a contradiction to the first law, but it's actually not. They are both true at the same time. So this one says, when two elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in a ratio of small whole numbers. Okay. So that sounds a little bit complicated. It is a little bit more complicated than the law of fixed proportions. And what we're saying here is if you have more than one way to combine them, essentially they combine in like a way that makes a whole multiple. So these were all, from this first example, were all of the same compound, but we have different compounds in some cases. So for example, we have two compounds that have copper and chlorine. So in one of them, you have 1.116 grams of chlorine to every gram of copper. And the other one, you have 0.558 grams of chlorine for every gram of copper. So, and again, you don't have to remember that. You would be given this sort of information if you needed to know it. But when you divide those, when you divide the 1.116 by 0.558, you get 2. And that seems like, okay, that's maybe important. But what's really important is that happens every single time. So when you have, so here we're looking at copper and chlorine. When you have, I'm going to just say copper and oxygen, you get a ratio. It's also ends up being a 2. In some cases, you might get a 3 or other numbers. But when you have more than one possible compound, they always end up as the same ratio. Um, and so here we're showing examples of those two compounds. So one of them happens to have a green color, the other one happens to have a brown color. We're showing here the way in which the atoms are combining to make that happen. Now, I say that, but at the time that this law was proposed, they didn't um, they didn't think about atoms as being the reason why. They just said, "Oh, this is very interesting that this is true, that we can do the math and come up with this." So those are the two laws: multiple proportions and definite proportions. And so, based on that information, essentially just that information, there wasn't a whole lot more than that um, that he had to go on. Dalton proposed this atomic theory. And the word atom was sort of, he pulled that from ancient Greek philosophy. I don't know a lot about ancient Greek philosophy or otherwise, but essentially they didn't really do experiments the way we would understand that today. Partly they didn't have that kind of technology, but they came up with ideas about how the world might be, and then they argued about it. And I'm not a philosopher, so this is just everything I say about this is probably from a chemistry textbook somewhere. So one side of the argument was that everything's somehow made up of this indivisible thing called an atom. And the other side of the argument was no, everything's made up of like continuous. If you keep breaking it down, it's sort of like water or mud where it all kind of flows together. So Dalton basically went back to this idea of atom from the Greek to describe what he thought was going on based on the evidence from these two different laws that had been discovered. And we showed the picture of the copper and the chlorine and how they were bonded. That is from this theory, right? So they didn't know that when they came up with these laws. But the theory has a few postulates, so let's go ahead and read those. So the first one, matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change. Okay, so we've kind of introduced that idea already in the first module, that things are made of atoms. And then the second part of the second postulate of the theory says an element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. A macroscopic sample of an element contains an incredibly large number of atoms, all of which have identical chemical properties. Okay, so a second postulate from the theory. We'll come back and look at the pictures, but I want to go through each of these postulates first. Third one, atoms of one element differ in properties from atoms of all other elements. Okay, and then the fourth one, a compound consists of two or more elements combined in a small whole number ratio. In a given compound, the number of atoms of each of its elements are always present in the same ratio. And then I think this is the last one. Yeah, the fifth one, atoms are neither created nor destroyed during a chemical change, but are instead rearranged to yield substances that are different from those present before the change. Okay, so these are the postulates of the atomic theory. So the idea at the time was sort of a novel idea. Well, not novel, of course, the Greeks had the idea too, but novel in the sense of experimental evidence was leading to this idea, which was those two laws. Why is it that every water has the same number of hydrogens and oxygens, and why is it that every different combination of two different elements leads to this multiple proportion? The simplest idea that made sense was that you have these atoms of the elements that are combining to make the compounds. And they didn't know at the time how small these atoms were, but they knew they were very, very, very small. And you needed a lot of them to make something. Here we're showing if we have a penny prior to 1982, they were completely made of copper. And so we're showing, okay, if you zoom in, you would see all of these copper atoms. They're all identical. They all have the same properties. And when we say the same properties, we mean things like the mass of each of those atoms is essentially the same or very close to the same. We'll talk about some variations there in a later section of this module. They have the same identical chemical properties. They would all react in the same way, so that you end up with these definite proportions. And those properties are different from other atoms. Other atoms of other elements would react in completely different ways, or very different ways, not always entirely different, but will react differently. So here we're showing some examples of some reactions. So here we have just pure copper. If we react it with oxygen, we get this copper oxide. And we'll talk about the naming of it later in this module. So we get this copper oxide complex or compound that has both copper and oxygen atoms, and it has them in a very specific ratio. And it, in this case, happens to be 1:1. And then these atoms are never actually destroyed. They're just rearranged. So going from copper to copper oxide, we're not breaking anything. We're just rearranging them. And this goes back to actually not one of these two laws, but the law we saw in the previous module, the law of definite proportion, or law of conservation of mass. So law of conservation of mass, law of definite proportions, law of multiple proportions are the ideas that led to this atomic theory. And here we're showing that reaction to get that copper 2 oxide, where we have some copper, we have oxygen in the air above it, and after the reaction takes place, we have this new substance. So again, we're showing macroscopic and molecular level observations of what this would look like. Okay, so this is the atomic theory. Now, in terms of what you need to know, I'm not going to ask that you write out word for word the exact definition, but you want to recognize if a statement is consistent with this theory, or is somehow inconsistent with it, or how this relates to things that we already know. So a lot of these ideas we actually talked about in Module 1, or they are ideas that you are already somewhat familiar with. So when we can look at, testing it, we would see, okay, when we start out, we need to have the same number of atoms at the end as what we started with. We're not really showing that here exactly. And here you're kind of showing maybe a better example of that. And when that happens, you end up with these compounds that have a specific ratio, and that's why we have, the law of definite proportions. And the law of multiple proportions follows from, okay, if each atom of each element is about the same mass, then you're going to have these, multiple proportions between the compounds that they form. So this idea was, we're showing all of these ways of representing atoms, and we've all kind of grown up with the idea that atoms are true. But this idea from the 1800s, so I think the exact date is listed here somewhere, 1807. So it's a little over 200 years old, this idea, but it's something we've accepted as fact for a very long time, long before they first saw those atoms with a scanning tunneling electron microscope in, I believe, in the 60s is when that first happened. It was very, people, all scientists believed in atoms prior to that, and it was just, okay, yeah, there they are. We knew we would see them someday. So that's the idea of atomic theory. And that's the focus of this first section. So you can feel free to continue on to module section 2.2.